we discuss how the different failure detectors are related according to the reducibility relation. So let us look to trivial reductions. We know that diamond P is reducible to P because P is always strongly accurate, thus it is also eventually strongly accurate. Next, S, if you remember S, it is a failure detector which has weak accuracy, and weak accuracy means there is always one correct process that is never suspected, and S is weakly accurate, thus it is also eventually weakly accurate, which is diamond S. So we are okay with this property. Next is S is always reducible to P. P can always implement S, because if you are strongly accurate against all processes, then you are also strongly accurate towards one correct process. So P is always strongly accurate, thus it is also weakly accurate. So we've done this property. And then, in the same way, the eventual counterparts are the same. So diamond S is reducible to diamond P. Diamond P is always eventually strongly accurate, thus it is also eventually weakly accurate. So these were the failure detectors with strong completeness. We have a set of failure detectors with weak completeness. If you remember weak completeness, what it says, that any process that has crashed or failed will be suspected by at least one process. These are the weakly complete failure detectors. So by the same token, diamond Q is reducible to Q. Q is always strongly accurate, thus it is eventually strongly accurate. Diamond W is reducible to W, since again W is always weakly accurate, so it is also eventually weakly accurate. By the same way, W is reducible to Q. Q is always strongly accurate, thus it is always weakly accurate. We cover this. And diamond W is reducible to diamond Q because diamond Q is always eventually strongly accurate, thus it is also eventually weakly accurate. So we cover these relations. Now, what we are going to do now in a number of slides is to show that completeness is relevant, in the sense that strong completeness and weak completeness are equivalent. First of all, any failure detector with weak completeness is trivially reducible to a failure detector with strong completeness. And I think this is easy. So what we are saying here, if we have a failure detector that is weak complete, then it can be always implemented using a failure detector that is strong complete. So this is trivial. We will show soon that strong completeness is also reducible to weak completeness. And by this, we get the following interesting property. First, that we can get strong completeness from weak completeness. It means P is reducible to Q, S is reducible to W, diamond P is reducible to diamond Q, and diamond S is reducible to diamond W, and thus they are equivalent. So P is equivalent to Q, S is equivalent to W, diamond P is equivalent to Q, and diamond S is equivalent to diamond W. So let us now prove the following. What we want to prove is that if we have a failure detector that has the weak completeness property, then we can use this failure detector to implement another failure detector that is strong. And this is what we want to show now. So let us see. So weak completeness ensures the following, that every crash is eventually detected by some correct process or node. And here is the basic idea, how to implement a strong complete failure detector using a weak complete failure detector. So every process Q broadcasts its suspicion set periodically to all other processes. Whenever a process receives a suspicion set from process Q, it does two things. It adds S to its suspicion list, and it removes Q from the suspicion list because Q has just communicated with it, so it is alive. So again, this works like a heartbeat because we remove Q if Q was in the suspicion list. Now, so eventually what we say here is that every crash is eventually detected by all correct processes because the suspicions are disseminated, so whenever a process detects a failed process, that is propagated, so every crash is eventually detected by all correct processes. The question now, which is more important, is that can this violate the accuracy property of the failure detector? We have two possible accuracy property. One is strong accuracy and the other is weak accuracy. So what we show now is that strong and weak accuracy are not violated. First, strong accuracy. So whenever a process disseminates its suspicion list, it is never inaccurate. So no one is ever inaccurate. Thus, our broadcast never spreads inaccurate suspicions, and therefore we maintain strong accuracy. So let us look now to weak accuracy. So everyone is accurate at least about one process, because weak accuracy says there is one correct process that cannot be suspected by all processes. So everyone is accurate about at least one process. Therefore, no one will spread inaccurate information about that specific process that is correct. Thus now, if the failure detector is strongly accurate or weakly accurate, these properties are maintained. By the same token, or the same method, eventual strong and eventual weak accuracy are not violated, and the proof is almost the same. So eventually, all faulty processes will be detected and inaccurate suspicion undone. So we'll get heartbeats from correct nodes and revise our decision. But eventually everything works as in the case of strong and weak accurate failure detectors. So what do we have now? So here what we have is the picture that we had before, and now we can add the equivalence. So we get this very nice cube with equivalences here and reducibility there. There is one failure detector that we want to add here, which is the eventual leader election omega. We said the eventual leader election is also a failure detector. So can we implement diamond S, the eventually weak failure detector with omega. So here is the question is, can be put this way. Can we implement diamond S if we are given an abstraction that implements omega and we use it to implement diamond S? Is this true? Here is how we implement diamond S. We suspect all processes except the leader given by omega. Omega gives a leader. Say this is the leader, so that's what we use. We suspect all other processes except that one. What about eventual completeness? All nodes are suspected except the leader, which is correct. You can suspect more nodes than necessary. Completeness does not prevent that. More interestingly is the eventual weak accuracy. Eventually, one correct node, which is in this case, it is the leader, is not suspected by anyone. And that is a correct implementation of eventual weak accuracy. Thus, we have that diamond S is reducible to omega. We have shown that diamond S is reducible to omega, but it turns out that also omega is reducible to diamond S. There are different ways to prove this, but here is one way. So there is a famous result relating failure detectors to the implementation of consensus that we are going to discuss in the last week by Chandra, Hatzilokos, and Tuwig. And the result says the following. If consensus is implementable with a failure detector D, then omega can be implemented using D. So if this is our consensus problem, if it is implemented by a failure detector D, then omega is also implemented by our failure detector D. Now, since diamond S, the eventually weak failure detector, can be used to solve consensus, and we are going to show that. So now if we can replace this with diamond S, and diamond S is, we replace D by diamond S in both cases here, then using this result we have shown that diamond S can implement omega. In fact, the result also implies that diamond W, we have shown, which is equivalent to diamond S, is the weakest failure detector to implement consensus. Thus, we have this very nice picture now. This is what we had before. And now we can add omega to this picture. So here we have the whole relationship between failure detectors, including the omega leader election abstraction.